Okay, so starting from where we left off, we wanted to see how to use nonlinear transforms without physically transforming data to Z-space. So remember, if we're trying to train a support vector machine in our original input space and we don't want to, or we can't get a hard margin, in other words, there are some examples that don't satisfy the constraints, and we don't want to settle for a soft margin, we can very well find a support vector machine that does work in a higher dimension. And these higher dimensions can be thousands or millions of dimensions more. And so it's, in a lot of cases, just computationally infeasible to try to find an SVM in that space. But again, it's attractive for us because there's a hard margin support vector machine in that we can use to classify new examples. So we just want to see how we can sort of extract what we want from that Z space without actually going there. And so we've already seen the primal problem. This is the optimization problem that gives us our optimal weights, which we can use to find our hyperplane or our separator. And so what we're doing is we're minimizing the norm of the weight vector subject to this constraint. The constraint is that we want correct classifications for all input examples. And so you can see that this problem is formalized in terms of the original input data. So all that means, or the consequence of that, is if we want to transform x into a higher dimension, we'd have to carry around these large vectors, which is computationally, as I said earlier, can be infeasible if we're going to dimensions that are orders of thousands or millions more. And just to give you a practical example, so if we were trying to, say, train a support vector machine that could be a binary classifier for, say, Twitter data, and we took tweets and we made sure each tweet was had 20 words, that would be each example would have vectors of length 20. So our x would be of length 20. And if we wanted to do a transformation on that, we could take it to thousands or millions more. And so those vectors would balloon into that number, thousands more. And again, it's attractive for us because what if we used our Twitter, or we tried to train our classifier on Twitter data, and we couldn't find an optimal hyperplane. But there did exist one in higher dimensional space. So we want to try to do that. But the problem here, and the point I'm trying to make, is that there's this dependence on the dimensions of the data set in this primal problem. We specifically D+1 optimization variables, W, our weight vector, and B, our bias. Remember, we get our weight vector by using our inputs, our X vectors. And so if there is some way to get rid of the reliance on the dimensions of the data set, then we could possibly take this same procedure to higher and higher dimensions and find an optimal hyperplane in that space. And so it turns out that there's an equivalent problem called the dual problem, and there's proof that shows this. Basically, it introduces these new alpha variables, which sort of help pin down this constraint, which is where the computational burden is. And once we run this procedure, both we run as quadratic programs, but when we run this dual problem, it outputs alpha n stars. And we can then use those alpha n stars to construct our optimal weight vector. In other words, we take the results of this problem and plug it into the primal problem, and then we can get the answer relatively easily. And so, yeah, we can get our optimal bias as well. And we have to select one of the support vectors, one of the alpha stars from our output. And so the significance of the problem is that of doing this is that we have swapped out the dependence or the dimensions for n optimization variables. N is just the number of training examples that we have, and we call those variables alpha because those are the variables we're introducing. And so the whole point of this is that we have this nice optimization problem that's equivalent to what we really want to solve, and so we can solve this problem, then we can solve the primal problem. And however, there is an implicit constraint or an implicit dimensionality dependence here in taking the dot product of these two x vectors, which is used to construct our optimal weights. Our optimal weights are used to construct or to find our hyperplane that does the classifications. And so if we could completely get rid of this dependence, then we have completely gotten rid of dimensionality dependence for a support vector machine, giving us the ability to possibly go to infinite dimensional spaces, which is pretty neat. So this is the proof that shows how the dual problem is equivalent to the primal problem, the Lagrangian. I don't think it's important for us, but I'll just basically say what it is. So this Lagrangian, we want to try to minimize with respect to B and W, while at the same time maximizing it with respect to alpha being greater than or equal to 0. This equation is sort of like reorganized from these terms above. We want to minimize our weight vectors. You see that here. And then we introduce the Lagrangian terms of these Lagrangian multipliers subject to our constraint. The constraint is just rewritten from being greater than or equal to 1 by subtracting 1. Or subtracting the constraint from 1. And so we'll just quickly see how the dual problem can be used on the example we saw earlier. So again, we have an x and a y. We multiply those two matrices to get xs, and then we can get g by multiplying xs with xs transpose. We initialize the variables necessary for our quadratic program, and this A matrix, the C matrix, and this P matrix. And then we run the dual SVM with this quadratic program, and then we get a much simpler equation to compute the optimal weights. But remember, there's still, and this is the resulting hyperplane or the support vector machine in whatever space. And so remember, there's this implicit dependence still, because in order to construct our optimal weights, we have to compute the dot product of these two x vectors here, x transpose, xn transpose, and xm. And so if we could just find a way to take the dot product without visiting the space or carrying around those big z vectors, the transformed x, then we could find these optimal weights with no dimension dependence. And so we realized that the dual SVM is just an inner product algorithm, where also known as GNM, which we saw earlier. And so we realize the dual SVM is an inner product algorithm where we want to, again, compute this dot product of the two transformed x's. We call them these new z vectors. And so we define this unique kernel function that tells us how to compute an inner product in z space. And so it's very actually simple function. Takes x and x prime, and it transforms each of them and takes the dot product of those two transformed vectors. And so the kernel function implicitly knows what the dot product is, or can find the dot product in a higher dimensional space without actually doing that transformation. And that's why, and that's sort of how it's done. So if you just take this this k and you plug it in to this equation, then you've completely removed the dependence on the dimensionality of the nonlinear transform, and you can go to even infinite dimensions to find an optimal hyperplane, to find a sport vector machine, and that's pretty impressive, pretty magical, if you ask me. And so this down here is sort of a demonstration of how the transform works. I'm going to try to demonstrate that in class. And then in our collaborative learnings, I think we'll see we'll practice problems that that show how we can do this, how we can even transform our x vectors into infinite dimensions and extract a hard margin classifier. Thanks.